Today we are breaking down Hermes KV cache as hierarchical memory for efficient streaming video understanding. This is some fresh research coming out of Fudan University, the Shanghai Innovation Institute, and the National University of Singapore.
And if you're an ML engineer, especially if you're working on multimodal models, this is one you really need to pay attention to. It tackles the streaming video bottleneck head on.
Okay, let's just get straight into it. Yeah. For everyone listening who's deep in the tech, what's the elevator pitch? Why should we care about Hermes?
All right, so the headline is really three big things. First, and this is the big one, it's a training-free architecture.
Meaning you can just plug it in?
You can plug this into Alavi or Quen right now, no retraining. Second, it pretty much eliminates out-of-memory errors when you're dealing with infinite streams.
Which is a classic problem. Okay, and third?
It achieves a 10x speedup in time to first token.
A 10x speedup? Without retraining, how's that even possible?
It's possible because it fundamentally changes how we manage the KV cache. See, Hermes stops treating the cache as, this one uniform block of data. Instead, it thinks about it hierarchically. It treats the shallow layers like sensory memory, super biased towards what's new, and the deep layers become long-term memory, where it holds onto these key semantic anchors.
So you're saying it aligns the cache strategy with how the model already wants to think.
Exactly. That's the core insight.
That is a massive claim. Okay, let's really unpack the engineering behind this. I mean, everyone knows offline video understanding is it's pretty good now. You upload a file, the model does its thing. But streaming?
Streaming is a completely different beast. It's like the difference between reading a book at your own pace versus trying to read a stock ticker that just never, ever stops.
Because the data just keeps coming. There's no end to it.
Right. And that gets you to the sliding window problem. In a standard multimodal LLM, you've got a fixed context window. The video, it just eats tokens for breakfast.
A single second can be hundreds of tokens.
Hundreds. So in a continuous stream, like from a security camera or a robot's vision system, your token count is basically infinite.
And that's when you hit the GPU wall, your VRAM fills up, and boom, OM error.
Exactly. And until now, you had two pretty bad choices to deal with this.
Right.
So option one is external memory. You offload the old video chunks to the CPU, maybe to a disk. Things like ReKV or Live VLM do this.
But that creates latency, doesn't it?
Huge latency. Because when you ask a question, the model has to stop, go fetch that data from the slower memory, and then refeed it into the system.
And if you're trying to have a real-time conversation with the model, that lag just kills the whole experience.
It's a deal breaker. So that's option one.
Okay. What's the other bad choice?
Aggressive compression, which basically means you just start deleting old tokens from the KV cache to make room for new ones.
The FIFO method, right? First in, first out?
Yep. The goldfish strategy. As soon as a new frame comes in, the oldest one just gets kicked out.
It's efficient, I guess, but it's not very smart.
It's dumb. If the most important clue in a video happened 10 minutes ago, well, it's gone. You deleted it to make room for, a shot of a blank wall the camera is staring at right now.
So you have the hoarder approach, which is really slow, and the goldfish approach, which is forgetful.
And Hermes tries to be the smart curator. The researchers realize that all these existing methods, they just apply a one-size-fits-all strategy. They treat layer 0 the same way they treat layer 30.
They're assuming every part of the transformer values information the same way.
But they don't, and this is my absolute favorite part of the paper. They did what they call a mechanistic attention investigation on Elevate OV7B.
So they popped the hood.
They popped the hood and basically watched the attention weights layer by layer as the model was processing a live stream.
Like watching a brain scan of the model. So what did they find?
They found this incredibly clear hierarchy that falls into three distinct categories. First, when you look at the shallow layers, like layer 0, layer 1, right at the bottom, they saw this intense recency bias.
Meaning those layers only care about what's brand new.
Exclusively. The attention just spikes on the newest frames and then immediately decays to almost 0 for anything older.
That makes a lot of sense intuitively.
Yeah.
Layer 0 is closest to the raw input. It's basically the model's eyes. It's just trying to perceive the pixels coming in right this second.
Exactly. The authors call it sensory memory. It's just capturing the raw visual signal. It doesn't care about the plot. It cares about image fidelity.
Okay, so that's the bottom of the stack. What happens as you go deeper into the model?
That's where it gets really interesting. When they got to the deep layers, think layer 26 out of 32, the behavior completely flipped. The recency bias was almost gone.
And what was there instead?
Instead, they saw these sparse Rhythmic spikes in attention that just persisted over time.
Rhythmic. What do you mean by rhythmic?
Yeah, so they noticed the spikes were appearing exactly 196 tokens apart.
Wait, for LEOAV, isn't 196 tokens the exact size of one encoded video frame?
Spot on. That's exactly it. The deep layers were naturally finding and latching onto specific anchor tokens that were summarizing entire frames. They weren't trying to keep every single pixel.
Whoa.
They were selecting these representative tokens that held the semantic meaning of that frame.
So layer 26 is acting like long-term memory. It's storing what happened, not the raw visual data of what it looked like.
Precisely. And then right in the middle, around layer 8 or so, they found a kind of working memory zone. It was a transition area, balancing a little bit of recency with some of that longer-term semantic history.
This is fascinating.
Yeah.
It implies the model wants to organize information this way. But if you just use a standard FIFO cache, you're forcing this flat memory structure onto a process that's naturally hierarchical.
We were basically fighting the model's nature. We were forcing layer 26 to keep recent, irrelevant junk it didn't care about and telling layer 0 to hold onto old data it had no use for.
So Hermes is the architecture that actually formalizes this observation. How do they do it? I mean, how do you implement this in the KV cache management? You can't just tell the model to be more human.
No, you have to code it right into the eviction logic. So they have distinct strategies for each layer group. For the shallow layers, the sensory memory, they use an exponential forgetting curve.
Ah, this is where they reference Ebbinghaus, right? The classic psychology
The
style.
very same. Ebbinghaus's forgetting curve says memory retention drops exponentially over time. So Hermes just applies that mathematically to the shallow layers. If a token is old, its importance score basically falls off a cliff. Evicted.
Simple enough.
Yeah.
You can't do that for the deep layers or you'd lose the whole plot.
Correct. So for the deep layers, they completely ignore time. Instead, their importance metric is based purely on attention magnitude.
Okay.
Since they know these layers are naturally focusing on those anchor tokens, the Hermes algorithm just scans for tokens with high attention weights.
So if layer 26 thinks a token from an hour ago is important, meaning it's paying a lot of attention to it, Hermes keeps it no matter how old it is.
Exactly. It just pins the important moments in the cache and lets all the noise fade away.
Okay, I can see a potential engineering problem with that, though.
What's that?
Well, if layer 20 decides a token is super important and keeps it, but layer 19 decides it's garbage and deletes it, doesn't that break the network? These layers feed into each other sequentially. You can't just have a gap in the signal path.
That is a classic issue in sparse models, and you're absolutely right. If you create these little islands of memory, the whole reasoning capability of the model just collapses. So Hermes addresses this with something they call cross-layer memory smoothing.
Okay, how does the smoothing work?
It propagates the important scores from the deeper layers back down to the shallower ones. So basically, if the brain, the deep layer, says, hey, this token is critical for the long-term context, it sends a signal down to the senses, the shallow layer, saying, hey, don't throw this one away yet, I still need it.
So it forces a kind of consistency check across the stack.
Yes. They use a smoothing hyperparameter, they call it lambda, to control just how much influence the deep layers have. It ensures that the visual memory stays aligned across the entire depth of the model, so the forward pass doesn't just hit a dead end.
Now, even with all this smart selection, you're still eventually evicting things to stay within that fixed VRAM budget. So when a token is finally pushed out of a deep layer, is it just gone?
Great question. No, they use summary tokens. In the deep layers, when tokens are finally evicted to make space, they aren't just deleted, they're aggregated into a single summary token for each compression step.
So it's like creating a little .zip file for the scene you just deleted.
That's a great way to put it. It preserves a compressed representation of that long-term memory right there in the cache. And this turns out to be really crucial for performance on these super long context benchmarks, because you maintain a trace of the history even if the granular details are gone.
There's one more technical nightmare in streaming I want to bring up. It's sort of the silent killer of these long context models. Positional embeddings.
Oh, the index outer bounds error? Yes.
Right. I mean, if you train your model on 4,000 tokens, but you're streaming for an hour, your token index might count up to like 100,000. The model has never seen the number 100,000 in its training data. It usually just starts hallucinating or crashes.
It creates a huge distribution shift. The math just breaks down because the positional encoding is so far outside the range the model ever learned. Hermes solves this with something called position reindexing.
How does that work in practice?
As tokens slide out of the cache or get summarized, Hermes dynamically remaps the indices of all the remaining tokens. It forces them to always sit within a contiguous range from 0 up to M, where M is your cache budget.
So if my budget is, say, 4,000 tokens, the model always thinks it's looking at a sequence that's only 4,000 tokens long, even if we're 3 hours into the stream.
Exactly. You're basically tricking the model into staying within its trained comfort zone. And the paper points out this works for both the standard 1D ROPE, which LLaVA uses, and the much more complex 3D MROPE that you see in models like Qwen 2.5 VL.
You know, that adaptability to MROPE is actually a pretty big deal.
It really is. Implementing reindexing on 3D rotary embeddings is not a trivial task. You've got to handle time, height, and width dimensions all at once. The fact they solve this in a generic way is a huge plus for anyone looking at their code base.
Okay, let's get to the scoreboard. They tested this on LLaVA and Qwen 2.5 VL. We mentioned the 10x speedup in the intro, but let's dig into those efficiency stats.
The metric that really stands out is TTFT time to first token. In a streaming setup, that's the lag between you asking your question and the first word appearing. Hermes keeps this consistently under 30 milliseconds.
30 milliseconds. That's basically instantaneous. How does that compare to the retrieval-based methods like RightKV?
Oh, those can take hundreds of milliseconds, sometimes even seconds, because of that retrieval overhead. They have to fetch the data, reprocess it, and then generate. Hermes has almost zero overhead when a query comes in because the cache is already perfectly curated. It's just ready to go.
And what about memory usage?
It's a flat line. If you look at the graphs in the paper, the standard methods show memory just spiking up linearly until the GPU crashes. With Hermes, it stays perfectly flat at whatever budget you set for it, 4 gigs, 6 gigs, whatever. You can run it indefinitely.
But here's the real kicker. Usually when you compress things this tightly, you pay a stupidity tax. You lose accuracy.
Yeah.
Did that happen here?
And that's the most counterintuitive result of the whole paper. On streaming benchmarks like Streaming Bench and OVO Bench, Hermes actually outperformed the base models in a lot of cases.
Wait, hold on. It performed better than the model that had access to more of the raw data?
Yes. Better. For example, on Qwen 2.5 VL7B, Hermes improved the accuracy by over 6% on some of these streaming benchmarks while using only 4,000 tokens of cache.
How is that even possible? How does less data give you a better answer?
Because in streaming, more data often just means more noise. If you just keep everything, the attention mechanism gets diluted. It's trying to pay attention to a million pixels at once. By using this hierarchical approach, Hermes is basically acting as a filter. It throws out the irrelevant visual noise and forces the model to focus on the high-value semantic anchors.
It's improving the signal-to-noise ratio.
Exactly. You're creating a cleaner signal for the model to reason over. And this was especially clear in what they called backward tracing tasks.
Give me an example of one of those.
Okay, so these are questions like, where did the exploration take place earlier? Or what color was the car that passed by 10 minutes ago?
Oh.
Because the deep layers in Hermes preserve those specific anchor tokens from the past, it could answer those questions with high accuracy.
Whereas a simple FIFO method.
A FIFO method would have deleted that scene maybe 20 minutes ago. It's just gone. Hermes kept the concept of the scene alive in its deep layers, even if the pixel-perfect representation was gone.
And to be thorough, I assume they ran ablation studies to prove this wasn't just some fluke.
Oh yeah, they did. They systematically turned off the different components. When they disabled the hierarchical management and just did a global compression treating all the layers, the same performance dropped significantly.
So that confirms it. The sensory versus long-term hypothesis isn't just a nice story.
It's not just a story. It's actually the optimal way to manage these weights.
I want to circle back to that training-free aspect as we wrap up, because that seems like the most important takeaway for any ML engineers listening right now.
It absolutely is. This requires no fine-tuning. You don't need to go gather a huge data set and burn GPU hours retraining LLaVA or Qwen. You can take an off-the-shelf model, wrap its KV cache with the Hermes logic, and immediately deploy it for infinite streaming.
That lowers the barrier to entry by a massive amount. You could technically run this on consumer hardware if the base model fits, because you know the cache isn't going to grow and eat all your RAM.
Correct. And I think it suggests something pretty profound about the models we already have. Hermes basically proves that these LLMs might already have the capacity for infinite streaming built in.
We just needed to manage the model's internal memory in a smarter way.
Precisely. We don't necessarily need massive external vector databases or complex RE pipelines for video. The capability is already there. We just had to unlock it with the right inference architecture. It turns the KV cache from a simple history log into an active semantic database.
And for anyone who wants to actually implement this, the paper mentions the code handles the reindexing for both rope and mrope. So checking out the GitHub repo seems worth it just for those code snippets alone.
I would argue that for any application that involves long-form video, whether it's security, robotics, video analysis, Hermes, or at least a hierarchical cache like it, is now the baseline. The efficiency gains are just too big to ignore.
It's really amazing. You realize how much performance is left on the table just because we treat memory as a flat list. Just by organizing it, you get a 10x speedup and better accuracy.
It really highlights that we're still in the very early days of understanding how these models actually think. We often treat them like black boxes, but papers like this show that if we can peek inside and design our systems to match their internal patterns, the room for optimization is just massive.
A perfect place to leave it. A huge leap forward for streaming video understanding and a really fascinating look into the brain of a transformer. Thanks for listening to this deep dive into Hermes.